Let me tell you something that has bugged me for years, and it should probably bug you too once you see what's going on. There's this line people repeat: teachers, textbooks, science channels, everyone, and they repeat it with this knowing smile, like they're handing you a little piece of cosmic wisdom. Light is both a wave and a particle. They say it like that's supposed to clear things up. But it doesn't clear anything up. It doesn't explain anything. It just gives you two wrong pictures instead of one. And because people keep saying it, students think they've learned something deep, when really they've just memorized a slogan. The truth is much stranger and much simpler. Light is neither a wave nor a particle. It's something else, something quantum, something that doesn't fit in any category you already know. And if you want to understand quantum mechanics, really understand it instead of living off mystical sounding hand waving, you've got to stop trying to force light into old classical boxes that were never made for it. Let's go back a bit, because the confusion didn't appear out of nowhere. Newton, for example, thought light was made of tiny particles, little projectiles, zipping through space. And if you lived in the 1700s, this actually seemed pretty sensible. Light travels in straight lines. It makes sharp shadows you can't see around corners. That's exactly what little bullets do. Waves don't behave that way. You can hear sound around a wall, but you sure can't see through it. So Newton had good reasons for his particle theory. Then Thomas Young comes along with his famous double-slit experiment. He shines light through two thin slits and sees something totally unexpected, an interference pattern. Bright and dark stripes, like you see with ripples of water. Particles can't interfere like that. Waves can. So people throw out Newton's idea and say, okay, light must be a wave. Then the 1800s come rolling in, and Maxwell writes down his equation. Easily some of the most beautiful mathematics any human has ever produced. And out of those equations pop electromagnetic waves, solutions that move at the speed of light. So the picture seems complete. Light is a wave in the electromagnetic field. Elegant, clean, done. Except it isn't done, because nature likes to play jokes on us right when we get too confident. At the turn of the 1900s, Planck studies black body radiation. Hot objects glow, and the spectrum of that glow simply does not agree with wave theory. It disagrees catastrophically, predicting infinite energy at short wavelengths. So Planck invents a trick, a mathematical adjustment, where energy comes in little steps instead of a smooth flow. He calls these steps quanta, and it works beautifully. But Planck himself doesn't believe these quanta are real, just a math patch, that's all. Then Einstein shows that these quanta cannot just be a mathematical convenience. They must be actual physical packet of energy, because only packets can explain why the photoelectric effect depends on frequency, not intensity. Shine bright red light and nothing happens. Shine dim blue light and electrons fly out. This only makes sense if light arrives in little packets with energy tied to frequency. Suddenly light looks like particles again. But then, just as suddenly, the wave-like interference experiments are still sitting there laughing ass. So which is it? A wave? A particle? The textbooks shrug and say, it depends how you look. Trust me, whenever someone says that in physics, something has gone wrong, the real story is that light is not choosing between being a wave or being a particle. Light is not switching costumes when you aren't looking. Light is a quantum object, and quantum objects don't behave like anything from the classical world. The mathematics that describes them doesn't talk about waves or particles. It talks about probability amplitudes, complex numbers with phases that evolve in time. When you compute with these amplitudes, sometimes the math looks wave-like because amplitudes add and can cancel or reinforce each other exactly like ripples. And sometimes the results look particle-like, because when you detect something, you get one discrete event, a single click in a detector, but these are just appearances. Neither one is the essence of the thing. The essence is the amplitude. Everything else is interpretation layered on top of it. Think about the double-slit experiment the right way. A classical wave goes through both slits. A classical particle goes through one or the other. But a quantum object doesn't do either of those things. Instead, it has an amplitude for going through slit A and an amplitude for going through slit B, and these amplitudes add together. Where the phases align, they boost each other. Where they oppose, they cancel. When you finally detect the photon, it hits one spot, one place, a single click. That looks particle-ish, but the pattern of where those clicks accumulate is entirely determined by the interference of amplitudes, which looks wave-ish. The photon didn't go through both slits or pick one slit. Those are classical ideas. The photon did what quantum objects do. It followed the rules of amplitudes. Nothing more, nothing less. And the funniest part, this whole wave-particle duality story doesn't even stop at light. Electrons do the same trick. Shoot electrons one at a time through a double slit, and they build up an interference pattern. These little guys have mass, charge, spin, everything that screams particle in a classical sense. Yet their amplitudes still interfere. So suddenly, textbooks start saying electrons are also waves. No, they're not. That's just repeating the same mistake twice. Electrons aren't waves any more than photons are. Atoms aren't waves. Molecules aren't waves. They're all quantum objects. It's the same category every time. And the moment you stop trying to cram them into the classical categories of wave and particle, their behavior stops being paradoxical and just becomes quantum. Weird, sure, but consistently weird in exactly the same way every single time. In classic physics, you had two bins to sort everything into waves in one, particles in the other. That's it. Two choices. But quantum mechanics doesn't fit either bin, and instead of inventing a new bin, we tried to shove quantum phenomena halfway into both. When things looked spread out, we said wave. When detection came in lumps, we said particle. But quantum mechanics is a different kind of machine altogether. The fundamental thing it gives you isn't a wave or a particle, it's an amplitude distribution. That's the actual object of the theory. You evolve amplitudes, you add amplitudes, you square amplitudes. Those three operations give you interference, quantization, discrete detection, everything. And once you use the mathematical structure as your actual picture of reality, you don't need the wave particle fairy tale anymore. And now we get to the part that really matters, the philosophical confusion. The moment someone hears light is both wave and particle, their brain starts inventing stories to make that make sense. People start saying mizu, remit determines reality. They start thinking consciousness collapses the wave function. They start believing the universe changes depending on whether you observe it. All of this nonsense grows from misunderstanding what quantum mechanics is describing. Quantum mechanics isn't telling you reality depends on who's looking. It's telling you that probability amplitudes evolve by certain rules. And when you perform a measurement, you get a discrete outcome. That's it. No metaphysics, no mysticism, no cosmic intellect, choosing paths. Just mathematics that accurately predicts experiments if I had my way of teaching this. I'd never start with waves or particles at all. I'd start by telling students, look, the classical world had two categories, but the quantum world forces us to invent a third one. The right objects to talk about are amplitudes. Then I'd teach them how amplitudes evolve, how they add, why their phases matter, and how probabilities come out of squaring them. And I'd show them the experiments, double slits, photoelectric effect, black body spectra, atomic spectra, all explained cleanly by amplitudes, no waves or particles needed. And you know what happens when you teach it this way? Students stop asking, is it really a wave? Is it really a particle? They stop trying to picture electrons as tiny beads or smeared out clouds. They stop imagining photons as little bullets sneaking through the universe. They start thinking in amplitudes. They start thinking quantum mechanically, and they stop getting confused. But of course, someone will eventually ask, okay, but what is an amplitude really? What is it physically? And the honest answer is, we don't know. Nobody knows. The amplitude might be a physical field. It might be information. It might be something else entirely. But whatever its deeper nature is, the mathematical object works. It makes predictions that match experiments to unbelievable precision. If someday we discover a deeper layer of reality underneath amplitudes, terrific, but we don't need one for now. The rules work. The experiments agree. That's physics. So once again, let me say it as plainly as I can. Light isn't a wave. Light isn't a particle. It's not both. It's not sometimes one, sometimes the other. Light is a quantum object. It behaves the way quantum mechanics says it behaves, and only looks wave-like or particle, like when we insist on describing it in terms borrowed from classical physics. If you understand that, really understand it, then you've taken your first real step into quantum mechanics. Not a mystical step, not a philosophical step, but a physical one, grounded in the calculations and experiments that actually matter. And if you stop trying to shove quantum objects into classical boxes, you'll find that the strangeness becomes comprehensible. The paradoxes evaporate, and the universe looks exactly as it should, not classical, not wave-like or particle-like, but fundamentally and beautifully quantum.